We are taking a journey to our massive neighbor, Jupiter, in an attempt to find a surface somewhere deep below its atmosphere. On Earth and on other rocky planets, we can easily imagine standing on solid ground. We expect planets to have a surface, a firm place where you could stand. But not all planets are built the same way. Our search for Jupiter's surface begins in the upper layers of its atmosphere. The outer layers we see through telescopes are made of thick clouds of gas, primarily hydrogen and helium, mixed with traces of methane, ammonia, and even water vapor. The first 30 to 50 miles of our descent take us through the visible cloud bands that give Jupiter its famous striped appearance. Layers of ammonia and other chemicals painted in reddish browns, tans, and whites. This cloud layer is bitterly cold, with temperatures around -145 degrees Celsius or -234 degrees Fahrenheit. As we continue downward through Jupiter's clouds, we pass through distinct zones and belts, moving in opposite directions. These clashing currents create violent winds and massive storms, with speeds reaching 400 miles per hour. And still, there is no solid surface, only thick clouds racing past in powerful, chaotic flows. As you descend 100 to 250 miles below Jupiter's cloud tops, everything changes rapidly. Atmospheric pressure skyrockets, crushing the surrounding gas to levels that equal, or even exceed, the pressure of the Mariana Trench, the deepest point of Earth's oceans, nearly 7 miles down. Here, Jupiter's atmosphere becomes far more complex, forming dense layered cloud systems under the immense weight of the gas above. Temperature rises alongside the pressure. The familiar ammonia clouds disappear, replaced by heavy layers of ammonium hydrosulfide. Descend farther, and you enter a hotter region dominated by water vapor clouds, fueling Jupiter's colossal lightning storms. These lightning strikes are up to 1,000 times more powerful than those on Earth, unleashing blinding flashes that rip through the planet's thick, churning clouds. At this depth, temperatures climb to 500 to 600 degrees Celsius, hot enough to melt many metals, while pressure becomes instantly fatal to a human. Yet even here, there is still no solid ground, only thicker, heavier layers of gas growing denser with every mile. Once you pass 250 miles below the clouds, Jupiter's atmosphere becomes so dense, it begins to behave like a liquid. This vast region stretches thousands of miles downward. As you sink deeper, hydrogen, the planet's dominant element, undergoes a dramatic transformation. Under crushing pressure, the gas is forced into a liquid state, beginning the transition toward metallic hydrogen, one of the most extreme forms of matter in our solar system. By the time you reach 2,500 miles beneath Jupiter's clouds, conditions become even more extreme. Over the next 10,000 miles, temperatures soar into the thousands of degrees Celsius, and pressure climbs to millions of times that of Earth's surface. In this immense layer of metallic hydrogen, atoms are squeezed so tightly that they begin to conduct electricity like a metal. This exotic electrified ocean is believed to generate Jupiter's enormous magnetic field, the strongest of any planet in the solar system. This layer is enormous, making up a large portion of Jupiter itself. Even this far down, there is still no solid surface. Instead, you would encounter something like a vast, crushing ocean. Liquid metallic hydrogen surrounding you completely, with nowhere to stand. Go even deeper, and you approach what scientists believe may be Jupiter's core, somewhere between 20 and 25,000 miles beneath the outer clouds of the planet. This region remains largely theoretical. There may be a solid or partially solid core made of rocky and metallic material, possibly wrapped in molten layers and intensely compressed hydrogen. Some scientists estimate this core could be as large as Earth, or even larger. For now, its true nature remains one of Jupiter's greatest mysteries. At roughly 25,000 miles down, temperatures soar to around 24,000 degrees Celsius, hotter than the surface of the Sun, while pressure rises to nearly 45 million times that of Earth at sea level. If Jupiter has a core, it would be buried beneath a dense, molten layer unlike anything we could ever explore. This deepest region may be the closest thing Jupiter has to a surface, yet no probe or spacecraft could even come close to surviving the crushing pressure and searing heat required to reach it. At these temperatures, no known material could remain solid for even a moment. Unlike Earth, where the atmosphere ends and solid ground begins, Jupiter has no clear surface at all. The planet is made almost entirely of gas and liquid, with no hard boundaries separating one layer from the next. If you tried to descend into Jupiter, you would never actually land. Instead, you would fall endlessly through thickening layers of gas that slowly behave like liquid, long before pressure and heat would destroy you. While reaching Jupiter's core remains impossible with today's technology, studying these layers helps us understand what makes gas giants so different from rocky worlds like Earth. Searching for Jupiter's surface is a journey into extremes. You would fall through freezing clouds and raging storms, pass into oceans of metallic hydrogen, and descend toward regions where pressure and heat become utterly unimaginable. Because Jupiter has no solid ground, the descent would never end, only intensify, until the crushing pressure and searing temperatures finally destroy you. It's the immense gravity of Jupiter, driven by its incredible mass of gas, that gives the planet its overwhelming power. Even outside its clouds, intense radiation would kill a human within hours. Descend deeper, and Jupiter's gravity forces pressure and heat to crushing extremes, making survival impossible long before any core is reached. There is no solid surface to land on, but by understanding Jupiter's layered interior, we gain a clearer picture of how gas giants work, and how gravity shapes some of the most powerful forces in our universe.